Good morning, everyone. Welcome to our first, regular spring seminar. So today we are delighted to have with us Dr. Mevin Hooten. He's a professor at Department of Statistics and Data Science at UT Austin. So not too far from us. He has a long and illustrious profile, so I'm only going to try to summarize a few things about him. So he's an elected fellow of the ASA, and he's also a previous chair of the ASA section on statistics and environment, and he has served and currently serving as associate editor of many journals, including Biometrics and Environmetrics, among others. And he has authored over 160 publications and also 3 books. And his main research interests are in Bayesian and spatio-temporal statistics, with applications in ecology and environmental science, among many other things. And today he's going to tell us about some interesting stuff regarding recharge dynamics with animal movement data. So please join me in welcoming Professor Hooten.
Thank you. That was great. You have an excellent memory. It's really good to be here. Thanks so much for having me. First of all, it's just good to be somewhere besides in my house. So thank you. If folks, as I'm going through this, if you want to stop me and interrupt, feel free to do it. I'll try to sort of control the time a little bit so that I can make sure I get through everything. The good stuff, of course, comes at the end. Those of you who know me at all know that I spend a lot of my time in the area of spatial and spatio-temporal statistics, and one of the big things that I'm interested in is mechanisms and making sure mechanisms are represented in our statistical models. And so that's kind of my thing, among others, of course. And so this is what this talk is about today. I got into this notion of modeling trajectories by kind of the back door. I came in through the space-time world, and traditional space-time statistics, modeling large Eulerian processes with models that describe dynamics at higher levels of organization than the individual level. And a friend of mine, Devin Johnson, who some of you might know, a statistician at NOAA, he introduced me to this idea of trajectories and thinking about dynamics of individuals as they move around. There's a lot of different names for this, and I'll stick to the animal movement name for it, but you could imagine, I'm sure, there's tons of trajectories like this in your work, and I know some of you are experts in stochastic processes and time series too, and this is all related, of course. This is just my view of it through the world of ecology. What else did I want to tell you before we got started? This movie here. I got a few movies for you. If they work, we'll see. These are greater white-fronted geese. There's some folks associated with Texas A&M that work on these. These are the Greenland subspecies. They're warming up here in staging grounds in Ireland before they're going to migrate to ultimately Greenland, but with a stopover at Iceland. And so we'll see a map that's bigger than this in a bit. I had a student, some of you may know Henry Scharf, who's a professor now. He's really interested in network models and understanding connections among individuals in these kinds of models. And I know you may have met with the Torren Schaefer recently, who talked about some of these ideas also. This will be from a slightly different perspective. It's just a motivating movie for you to take a look at, so I can set the stage here. Let me give you some background. So this is how this talk is going to work. I got to sort of, most people don't work with animal movement data, so I've got one of my jobs here is to help get you interested in it in general as statisticians. So that's kind of my purpose here. So to do that, I'll set the stage, and I hope you'll find this is a pretty accessible talk. This is not going to be too deep, right? It's just going to give you kind of my big picture feelings of how we can do better in this field. Here's one particular way we could collect these data. Just like we all have these things in our pockets, tracking us day to day, you know, the companies are doing that, of course. We're putting similar things on animals and allowing them to tell us where these animals are located at given points in time for a variety of different individuals and different species. These are our white-fronted geese. These have net colors, of course. You can see it has a telemetry device in there. This is a GPS telemetry device. So the type of data you might get from this are these data that you can see here on the screen. And I don't know if you can see can you see my hand there? Check the pointer. Okay, thank you. So this is Ireland down here. They're going to fly from here and migrate up to Iceland, where there's another staging ground, and then they're going to move on to Greenland after that. There's 4 trajectories shown here. And this is how I look at time series data, right, in space. This is how I look at it. So this is, you're going to see some maps like this. Different point colors, if you can make those out. I know they're kind of tiny for you there, represent different individuals. So we have 4 individuals here. Okay. That's a bit about the data. Let me tell you about the models. This was, to my surprise, when I learned about trajectory data, whenever that was, 15 years ago, for the first time. We started reviewing all the literature. We started writing papers in this area. And it wasn't until years later that I realized, oh my gosh, all these models for telemetry data that are out there that people use for animal movement fall into the exact same classes that they do in spatial statistics. So for those of you who teach or research in spatial statistics, you know that this is the way the procedure works in those classes. Almost always you start, or at least I do when I teach spatial, I start with point process models, then I move on to lattice models, and then I move on to geostatistics, and that's how it works. Exactly the same breakdown for the different types of models and telemetry data. And so when we were writing this book, that sort of, the purpose of it was really to collect a lot of this information so that I had it as a resource for myself. We put it all in the same notation, and one of the things I realized was, wow, this is exactly the same thing that I'm used to. So it's a place of comfort for me. So point process models, right? This is one of the ways people think about modeling animal telemetry data. This is this notion of like, these are points in space that are observed, and so we should model them that way and understand that. What gives them heterogeneity, what sort of probability distributions in space, in geographic space, give rise to these points that we observe. That's one way of doing it. Then you put the dynamics on that if you want. The other approach is this discrete time model. So obviously this would be more of like what were traditional sort of time series models, Markov type processes and other things that we could use to model trajectories. Of course, these are higher dimensional than just one. It's usually 2 or 3 dimensional at most. And then finally, these continuous time models. So, and this is a review, right? I told you this is an accessible talk. So this is the one I want to focus on for today, continuous time model. So we're talking about stochastic processes here. So the thing that I'll introduce next is just walk you through some real basics of that, because I know it's review for most people here, but for those of you, maybe students and others that haven't seen it, especially in the context that I'm going to talk about it today, I need to set the stage so we can get to some of the more complicated models later. Okay. Let's think about one main class of models called advection diffusion models. This is what I call them. You might call them something else, but Wiener processes would be another name for these things. You could imagine a position in space mu. This is what I'll call the location of an individual animal in space. I'll call that mu. So let's think about 2 dimensions for now, for mu. Indexed in time t. So the change in location, d mu, would be a function of some velocity, sigma in this case, and then some Brownian increment, or the Wiener increment. So this is like a white noise process over there, dB. This is just my notation. So I know it may be a little bit unfamiliar for you, but this is the way I'd look at it. So that would be our basic diffusion process. That allows animals to move around in 2 dimensions at velocity sigma, for example, in this particular case. It'll give us a picture like what we see on the top right there in terms of a trajectory. There's a couple of things to note about that. One is, yeah, that looks like we see a particle moving around just like it's supposed to in your first 101 stochastic processes class. It just happens to be in 2 dimensions, that's all. 2, it's a little bit too rough, not quite smooth enough to represent a real animal trajectory as it moves around in space for the most part. And that's part of the game, is allowing these things to be smooth enough to be realistic. But before we get there, let's continue on. The first sort of generalization you might make to a ODE, in this case an SDE type of representation of animal trajectory, would be to add an advection component to it. Right? So the advection bit, we're now on the middle left panel. You could think about it as sort of a gradient function associated with some underlying surface of interest. This surface I'll call a potential function, P. P you could think about defining in a lot of different ways. The simplest way to do it is probably that there's a surface in space. You think about individuals as like marbles on the surface, and as they roll, they might roll from uphill to downhill. They might roll toward from the top of mountains down to the valleys, et cetera. And then what makes up the surface itself, P, would be the thing of interest. Usually the inferential goal here would be learning about that, in addition to understanding velocity and maybe allowing for velocity to change over time. So that's the idea there. So what's a really simple potential function that you could use there? A simple one would be something like the one you see on the bottom left here, where there might be, this might be appropriate for an animal like a central place forager, where, for example, it lives in a certain spot and it branches out from there to find its food and do its daily sort of life history stuff. So there's a central place that acts as a parameter, in this case, parameter vector, C, and C might be something that we would estimate in this model that makes up the advection component. So, you know, advection and diffusion, if you're not used to these terms, diffusion is like smoke coming out of a smokestack and spreading out. Advection is like when the wind blows the smoke in a certain direction. We can use the same concept for animals as they move, except you might refer to it as drift for advection or bias or something like that. And the diffusion part, you might refer to it as motility. Just getting all the sort of terminology reconciled. Okay, so that's 101 on SDEs. Sorry for that. It's like your 101 stochastic processes class. But this is how it's used in animal movement models. And this has been popularized by statisticians we know. David Brillinger and others tend to use these models and write about them quite a bit. Okay. One of the things that these models, the ones I showed you just there, don't do inherently is they don't account for heterogeneity just in the diffusion process alone. And so we know there's a lot of different ways to write that. They also don't allow us to account for smoothness, as I said before. So what I'd like to do next, just setting the stage for what comes toward the end of the talk, is first develop a framework for the smoothness. And I'm not going to go into too much detail on that because I think these are well-known concepts in statistics, but let's use a process convolution approach where if you have an underlying process that's perhaps somewhat noisy, but correlated enough that it could represent and help us get at mechanisms moving animals from one place to another. If you smooth it out with a smoothing kernel, like this is just 1D, right? A 1D movement process. But this is one of Dave Higdon's favorite sort of graphics, right? You smooth that out, you can get all sorts of neat things that come out of this, and especially in the Gaussian process world where we can help use this kernel to define covariance matrices and whatnot that allow us to fit these models. So this is a great trick. And you don't have to fit these models using covariance perspective. In fact, I rarely do. Okay. Now, that takes care of the smoothness, right? You can smooth these things out a little bit by passing, it's like a moving average, right? Passing this thing across the time series. What we'd like to do is allow for heterogeneity in there also. So you can imagine certain individuals like our greater white-fronted geese fly from, they're on a staging ground in Ireland, they're kind of warming up, and eventually they migrate long, direct, very smooth trajectory, it's fast, to Iceland, and then they're hanging out in Iceland a bit, staging again before they head on to Greenland. And so we need something that can account for those changes in the dynamics over time. The easiest way to do that in a phenomenological way, the way statisticians might think about this, is to let this kernel, and this is what Higdon would do, I think, let this kernel vary over time, the width of it. That's the simplest thing I could do, right? Is increase the weighted the moving average, so it's averaging more stuff. We'll allow it to be smoother over time. If you narrow the kernel, it'll allow it to be coarser over time and allow for higher frequency dynamics in that period. Those are the ways you could do it. The problem with those ways, I think it's great. It's a great idea. Fundamentally, it's easy. We could generalize the model that way, no problem. The problem with it for me personally is I have one piece of software that I really like for fitting geostatistical model. This is, oh, by the way, that's all this is, right? It's a geostatistical model just in a time context, right? Just smooth the thing out. Do some kriging on the data. You pick the kernel though. That's the beauty of it. There's a lot of different ways to pick the kernel. I like my software for doing it, and it assumes homogeneity in time of this kernel. So the other approach that we could use is allow myself to use that same software, feed it in a change in the temporal domain. So feed in a warped version of the time domain, and that's how I'll introduce that on the next slide.
Basically, we have this equation and they just randomly smooth it. But how do you interpret that? Like, we have the differential equation, we can interpret it as movement of the animal. But once we smooth on it a little bit, it's hard to sort of interpret the movement.
Yep.
Once you change the actual measure, we'll do something with that to make the actual. So you can still model the actual movement.
Yep.
And
for sure. Great question. I took that slide out. Here's the deal. One easy way to do it is build a kernel that pushes this down one level so that you have an integrated movement model, right? And then you could envision the movement being on the velocity process itself instead of on the position process. Then it still has a mechanism, and it's important in that sense. But to start this talk, I'm kind of lacking a few mechanisms on purpose and allowing for some heterogeneity so that I can build up some models that we can talk about later. But yeah, the sky's the limit. You could do this however you like. The smoothing itself just allows us to get the smoothness right that matches the data. If you can build specific smoothing kernels or convolution kernels that make sense to you, that's great. That's what you should do. Back to the heterogeneity bit. Regardless of what kernel you use, what I'd like to do is allow us to have some heterogeneity in the smoothness over time. And it would be cool if that has some mechanism associated with it as well. So a couple ways you could do it. There was a sort of burgeoning field in spatial statistics. When was that? 10 years ago, where folks were really interested in spatial deformation approaches and to account for heterogeneity and non-stationarity in the spatial process. People would deform the spatial domain so that the model itself sees the points as being closer together, farther apart than they actually are in different regions, right? It became kind of a challenging mathematical problem to work with those models. And I think that's why folks went away from it for the most part. It's still out there here and there, but we said, well, why don't we use the same thing in time? So you could imagine a warped version of the temporal domain. Let's call that warp W. And you can see that down here in the bottom left. Let's stick with this one for now. Where the original time domain, the time points would be equally spaced, and that's the way that time works, of course. But all of our perspectives of time are slightly warped, and so you could imagine compressing time in certain regions and expanding it in other regions, and this function W would do that. You can build these functions in a lot of different ways. One way you could do it is you could allow it to be really general. Just warp it with where such that the derivative of that warping process looks smooth, but somewhat wiggly, I guess, would be the word for this. So it's very flexible way to say, well, in this region right here, we're going to compress when the derivative of the warp is small, and in this way, we're going to expand where it's where the derivative is big. And so it's a neat relationship between this warped version of time and the derivative and what it tells us about compression or expansion of time. None of this really matters other than what the model will see is WT, not T. And the beauty of that is that it sees this heterogeneity in it over time. And in fact, you could go one step further, back to this former question, and say, how could we make this more mechanistic? So one way we could do it is say, well, suppose that we're interested in warping a time domain that's really explicit, associated with some process that we know about in nature, like a migration. We know that things are going to be moving in one sort of dynamic before migration, then they're going to be actively doing a different sort of thing that will maybe lead to more smoothness, and then later it will return back to more of this sort of active type of dynamic. And so we could build specific types of temporal warps as long as we're careful not to break the one rule about warping time or space. You're not supposed to allow it to fold, right? That's the one thing about it. So be careful with these functions. You allow it to fold, you get into sort of a back to the future situation. The point is, you see what happens here, right? These bits in the middle become a lot wider, and so we've sort of expanded time right there, and it allows for more smoothness in the model. That's the idea. As far as the model knows, it's seeing time the way that time works, but it's allowing for heterogeneity. So you could imagine building a setup where you score a bunch of different warps, and that would help you identify which ones of those warps are more optimal or appropriate for the data that you have in hand. Or you could model average across them or whatever, or you could try to estimate them, which is where I think a lot of this gets stuck. Okay, so that's one way to do it. Let's see what happens with these greater white-fronted geese. In the bottom, on the left panel, in the bottom right, you've got Ireland, and on the top left, you've got Iceland. And so these 4 individuals are migrating between these 2 locations. You can see that I've shown on the top right the marginal trajectories for those, just so you can see what's going on there in terms of latitude and longitude. And in the bottom right would be the optimal inferred warping functions associated with, it's the derivative of the warping function, but associated with the migration. So this is kind of cool. It tells us a little bit about the life history of these individuals. For example, and some of these things may be obvious, but at least we're here formally quantifying it. For example, you notice this blue and red individual both leave approximately the same time, but the red individual, as we're watching, becomes disoriented out here. It's kind of very unusual behavior, by the way, for this species, for this to happen. And then eventually gets back on track and finds Iceland and moves around the coast. Blue individual takes more of a direct route between the two and moves obviously a little bit faster. You can tell it's moving faster because the inferred current warp is a lot, not a lot, but definitely wider for sure. About a week later, the next two individuals leave, the green one and the purple one. And they also, one of those takes more of a circuitous path to get there, and the other one takes more direct path to get there. And the green one, we infer that it takes longer for it to get there, obviously, because it's taking a longer route to get there as well. So this is cool. This is one way to get heterogeneity in the models that I would call very phenomenological. It's very statistical. We're allowing for, we're doing what spatial statisticians or time series statisticians do a lot. We're not necessarily thinking about mechanisms. We're just allowing for the smoothness and the heterogeneity to represent the processes that we're trying to study. And we could kind of infer something by making sense of some of the results of those. It's not my preferred way to do it. Did you have a question?
Yeah. So what's the data point that you? So I think it is like the model training. So what's the data point that?
Yeah, the data would be the points that I showed you at the beginning. These little points, if you can see them in here, they're locations, and let's call those things mu for now, but I observe them with some uncertainty, so S would be what I'll call those in a minute. There'll be positions in space at a subset of times. But we have a continuous underlying model, right? Continuous time underlying model. Okay, so this is one way to account for heterogeneity. So I just wanted to get you up to speed on that. This is kind of par for the course in this field. What I'd like to do is think about how to get more dynamics in it. And I'm not, or more mechanisms associated with the dynamics in it. I'm not the first person to come up with that idea. Turns out, long before we wrote our book, there was another book on animal movement that Aristotle wrote. And amazingly, you know, these folks were fantastic scientists back then. They didn't quite have the formalism that we have now in math and statistics to write about the details, but they knew what was happening and they understood it pretty well. And the point is here that Aristotle, current modern animal movement folks do things kind of the way that I suggested on the previous slides. You know, we'll represent the aspects of the data we think are important to represent so that we have a model that's a good fit. But, you know, it's a stretch to think about mechanisms maybe there. But they were thinking about mechanisms ages ago, and we should do that more. In fact, physiology, we have world-class physiologists at Texas A&M and at University of Texas, and they think about this stuff all the time. Why don't we do it in the quantitative analysis of animal movement data in the field then? So that was sort of the goal of a lot of what comes next. This is a mountain lion on a treadmill. My friends at Colorado Parks and Wildlife put animals on treadmills. And the reason they do that, in part, they do a lot of other things with them too that are somewhat odd. But the reason they do that is because they want to understand the energetics, right? If you can measure the oxygen rates and usage of the animal as it's moving in certain ways, you can understand more about the physiology of the animal and what its needs are in terms of energy, et cetera. And so one of many studies to do that, and this is how physiologists, animal physiologists do their work, right? But none of this makes its way into statistical models for animal movement in real settings. This is not a real setting, right? We want to know how animals move around in their landscapes and why they do what they do and try to learn about those processes. The one thing about energy is, and this is when we started really thinking about this, is that it's sort of cyclical, right? It works almost, not to simplify this too much, because I doubt there's any physiologists in the room, but it works almost like your battery does in your phone, right? There's a period where you charge the battery, and then there's a period where you use the phone and the battery discharges over time. Hence the recharge title in the talk, right? And so we started thinking, oh, that's kind of cool how that works, but that's never in any of these statistical models for movement. And we know that it affects the movement, and the movement affects that charge process also. So how can we formally get that in there? One of the ways is to think about some of these traditional models and just extending them in a way that can account for that. And that's what I'll talk to you about next. But we started thinking about other physiological processes we could get in there too, like the things like that are cyclical, like not just acquiring and then expending energy, but the need to sleep, the need to drink and hydrate, the need to care for young and other more complicated life history processes too. And so wouldn't it be nice if we had a modeling framework that would help us with that? That's what sort of led to this. So here was our idea, and this is just one way to do it. Again, my goal is to help get you convinced that these are important problems, and there's probably a lot of other great ways to deal with these things. Here's one approach that's relatively simple, I think. Think about a model for movement like we had before, and let's stay in continuous time because it's easy and we're sort of going on that theme here in this talk. But you could do this in other frameworks too, the point process framework or the discrete time framework. D mu now, the change in position over time, might arise from one of two different models. One model, not mu, but M0 or M1, the script M. One model, M0, might be when the animal is charged, fully charged, let's say. Charged means whatever you want it to mean. It could mean topped up on energy, it could mean hydrated, it could mean any of these other things, right? Fully rested. In that case, we might think maybe, this is all modeling decision stuff, but we might think the animal can move around kind of at will. It can do the other life history things that it needs to do in its life. It's going to move probably, and it's going to wander around, sleep, do this, go check this out, meet these other conspecific animals or whatever it needs to do, right? It would happen there when this underlying latent variable z is equal to 0. So we're going to set up a mixture model sort of framework here. And then M1 would be the alternative case where the animal needs to recharge. So what we're setting up here is a decision process. The decision process is Z. It's binary. It's saying, do I discharge or do I recharge at this given time? And that's Z. So Z would be the interesting variable to us if you wanted to learn about animal decision making. And we could imagine that as being a Bernoulli process over time, being driven by some underlying probability function, rho t. Rho t then is where the magic needs to happen. Rho t would be the thing that says, what is it that's causing our individuals to respond the way they are and make their decisions and how they're going to move. And then, of course, each of these two models that I've written super generally here would be parameterized however you like. They could be diffusion models, advection diffusion models. It makes a lot of sense for me to set it up so that the M0 model is a diffusion model and the M1 model is an advection diffusion model. That's what makes sense to me because the advection would be helping us take care of the animals making a conscious decision. I need to go recharge in one way or another. And so we would like to learn about what allows them to do that, how they navigate the landscape when they need to do that. So let me give you a graphical representation of what that might look like. This would be a period where the animal needs to recharge. Maybe it's heading toward a central place for some reason. Maybe it's a recharge patch. Maybe it's a place where it sleeps or nests. Then when it's filled up, it can decide to move and it sees the landscape in a totally different way. It's going to move maybe with a diffusive sort of process until eventually it runs out of charge, needs to recharge and heads back home. See how that works? That's what that model is capable of doing if we set it up right. So that's a pretty generic situation, just so you can see how it works. I'd like to show you a little more of a realistic schematic here, a cartoon for how we think it might work for a mountain lion, for example. Mountain lions are top food chain predators. They're carnivores, right? So they live for the most part by eating prey that consists of mule deer in the Mountain West, right? So these are like our white-tailed deer in Texas, mule deer. They will, let's say, go to certain places where they know that they can hunt for deer. They will capture deer usually. They will usually store it because they can't eat the whole thing at once. They'll keep that, it's called caching it when they do that. They'll store it, they'll cache it in a certain place. They'll leave that place, they'll wander around, do their other life history stuff, explore, go find other prey. And then they'll eventually circle back to that cached kill site when they don't find anything else. And so the idea would be that how do we account for that in these models? And you can see the schematic here. The trajectory would be in this blue line in the middle as they're walking along. The points along there would be our observations of where the individual is at that given time. Right, so the red and the green points along that blue trajectory, that's kind of just a heuristic for what might actually happen. As it's going, it's constantly making decisions about what it should be doing next. And at some point, let's say it gets hungry and it needs to recharge. So it decides to head toward a certain place where it knows it can either find food or it's already stored food there. It will stay there, it will eat up, it'll rest up whatever it needs to do, and it'll eventually leave that place and continue on its way. And it has to make a decision to change that at that point. What we'd like to do is infer all of that from only the trajectory data. If you have other data, like accelerometer data, for example, or some other biometric data, which they do have for these animals, that's great. Maybe you find a way to integrate that into the same sort of modeling framework. But for now, let's see if we can do all of that just from telemetry data. Positions are observations of positions of the individual over time. Okay. The key in this graphic is the process on the bottom. The very bottom line here, this rho t. This is the decision function, right? When rho t is small, it's not making a decision to recharge. When rho t is big, it is making a decision to recharge in this particular case. So we need to have a way to sort of parameterize rho t such that it's mechanistically meaningful to us. And here's how we'll do that. Imagine, so we're taking a step back, we're putting the movement process aside for just a second, and let's think about a physiological process. What's happening inside the animal as it's going about its life history? So imagine that we're still thinking about space and time together. We have spatial domain up here in this figure on the right, and we could imagine it in many different dimensions, of course, right? Whether there's this first map might correspond to elevation, second map might correspond to slope or something, some other aspect of the animal's environment. Trajectory, you can see this is just a placeholder here drawn on these maps. And then the last one, maybe this is a recharge patch or something, a place where the animal forages or eats or sleeps or does something like that, right? So these are just examples so you can see how it works. We'd call these things W. These would be positions, these would be maps associated with each position in space, mu. Okay, if we wanted to think about how those multivariate aspects of the landscape come together to influence the physiological state of the animal, we could think about combining them in various ways. The easiest statistical way to do it is with a linear combination of those things. So if you linearly combine them with theta, right, in your usual sort of regression framework, you could learn about that theta and it would tell us something then, hopefully. That is, if we could measure the physiological state, it would tell us something about the importance of these different aspects of the environment, okay, as it's moving. So W theta is the main controller then of this, what I would call this physiological landscape that the animal experiences. It's unknown to us. Only certain aspects of it are known, like the features of the landscape itself. Every individual may respond slightly differently, and every species then responds differently, even so. The key bit to this model, and again, there may be other ways to do this, but this is the way that came to mind for us, is to accumulate and lose, I guess, that some aspect of that physiological aspect of the landscape over time as the animal's moving. So as this trajectory moves around in this space here, so this is the combined physiological landscape in the middle, and you get to these different points, 1, 2, 3, 4, etc. We need a function that looks like this on the bottom, which I'm calling G. This isn't rho, this is G. What this is a charge function. It's like your battery meter on your phone, if you could watch it over time, right? That's G. And simply, the way we could think about it is as a line integral. As the animal's traversing this space and experiencing these different environments, some of these environments are going to give it resources that it needs to live and recharge, and other ones are going to take it away. As it moves, it's going to move through these areas that are more challenging to move through or whatever. And so we just write down the line integral there as this important aspect of a mechanism associated with this physiological charge. So GT is the charge process itself, down there on the bottom left. And we could think about that as starting somewhere, given the beginning of the time domain you're interested in studying, G naught, and that could be estimated. And then you'd have this line integral over the physiological landscape, W theta. So the unknowns in this equation would be theta and G naught. So now we have a model for the charge process and how it's just one potential model, but it is a model for the charge process and how as the individual experiences these different changes in the environment, how it's going to affect their physiological state. What we need to do now is connect it to the movement decision process, whether it needs to recharge or not. And then we already know there's movement models associated with when it is recharging, how is it going to move, and when it is discharging, how is it going to move. We already have that set up, and I'll put it all together on the next slide. You can see, though, what happens here in number one. At the one location, you're at this point in the curve where you're losing your charge, so you're discharging. At number two, you're charging up because they went into this recharge patch right here. At number three, you're really discharged because you're out here on this long sojourn through this environment that's not helping, not aiding a charge at all, but maybe it's still important for other life history reasons. And number four, you've gotten back into the recharge patch here, and so you're now charged up. So that's the idea. Okay, what comes next is really easy now. There's only one piece missing. We have to link this one to the movement model, and the way we do that is just say, if G gets big, that's the charge process is big, then the decision to charge or recharge is small. That's it. So rho should relate to G in sort of an inverse way, and that's it. You can pick how you'd like to do that, but the way we did it is we just said rho is equal to 1 minus some function of G. So here's the full model. I could have just showed this at the beginning and it would have been a punchline, right? So here it is. We observe ST positions of the individuals at times TI, let's say. Of course, there's a finite set of times where we observe the individual due to the limitations of the device that does that for us. Let's just say that we measure that with some error. And of course, there's more sophisticated ways to account for measurement error in telemetry models. This is a simple one to start. But there's a true position mu that we seek to learn about usually. So that'll be an unknown latent process of interest. This will be a hierarchical model. We have some uncertainty associated with that that can be accommodated by, a Gaussian or some other distribution that accounts for measurement error. That's sort of up to you. Then we have an underlying process model in this SDE sort of framework, continuous time stochastic process framework for movement. So d mu, the change in position, could arise from one of two processes, either a diffusion only process, this top one, sigma times the white noise kind of process over here, or you could have an advection diffusion process where the potential function is made up of another regression, x beta. Makes sense that we would use x beta, right? As the animal moves around in space, it's going to be responding to the environment in different ways as it goes, and that's going to affect the drift. So when it needs to recharge, for example, we're assuming that it knows how to do that in the landscape, okay? And the animals do know that. So other than that, we'll have some parameters in there. So sigma controls the velocity of a diffusing only sort of individual when it's not making the decision to recharge. When it is making the decision to recharge, we need to learn about beta, the effect of the environment on its drift or habitat selection, if you want. And also sigma 1, which controls the velocity in that particular case, in addition to whatever we get out of the drift function. And then that depends on an underlying binary decision process Z that's continuous in time, which depends on a Bernoulli with probability rho, and rho is connected to G, this recharge function that I showed you on the previous slide. You got multiple levels of the hierarchy here, but I think we've tried to construct it in a way that makes sense mechanistically. It's as close as I could get to something we could still fit statistically to data and learn about some of these unknowns that are in the model. So we got a couple sets of regression coefficients. We got a couple velocities we need to learn about, or things that control the motility of the animal we need to learn about, starting place in the recharge process, and some measurement error variance type stuff. That's it. It's not complicated. There's, in the order of 10 parameters, give or take, depending on the model you want to fit. Okay, let's see how this does with a simulated data set. I'll show you how it works. So let's simulate a data set under this sort of framework, this paradigm. In this case, here's a trajectory on the right that I'm showing you in 2D Euclidean space, geographic space. We've got a function in the background, this gray shaded region that's like distance to a recharge patch that's shaded in green here, colored in green, right? So it's a recharge patch. When the animal gets in the recharge patch, it likes what it sees, it can recharge in there, maybe it's food resources or water or something else, right? The G function, the charge function itself, you can see as the trajectory is going, you can see that it starts out low, it gets into the recharge patch, it starts to charge, et cetera, then it declines, then it increases again, et cetera. And then the decision process associated with whether it needs to charge or not is shown as rho right here. So you can see how it kind of mirrors the, not exactly, a bit more smoothness because of the functional form we use, but it mirrors the charge process itself. When we fit this model to data, so I'm not going to belabor that part, you can imagine there's a variety of methods we could do to fit this model. We'll use Bayesian methods. But that's because we can keep it in a hierarchical framework and we don't have to use an integrated likelihood or anything else to do it, but you probably could do it that way. Yep.
So your renewing process, is that IID from some subset of time, from some time frame?
It's continuous time Bernoulli,
Okay.
and it is IID conditionally on rho.
Mhm.
Yep.
But you can imagine the decision being dependent. You know,
For sure. There you go. Yep, yep. So if you like that, then put that dependence in this latent then on that Bernoulli process. Yep, for sure. Probably people, the individuals aren't switching back and forth instantaneously between making decisions. Or maybe they are. Or maybe every time you look at your phone, you're doing the exact same. Should I answer that email or should I go to this meeting? You know, I don't know. We could argue that. But no, for sure. Generalize it however you like. I think it's the concept here that's important. Great question though. Let's see what happens when we fit the model to these data. So before I show you this movie, let me explain what's going to come here because you're going to see several of these. On the top left, you're going to see the easting and northing associated with the marginal trajectory, right? So this is the margins in latitude and longitude, basically. In the gray, in every one of these graphics, you'll see the resource in the background. So what affects the movement itself? In this case, this gray line is distance, a representation of distance to the recharge patch, let's say, because we're going to keep it simple here. The G function is going to be the third time series you see. These are sort of longitudinal plots, right? So the G function will be the time series associated with charge, and then rho will be on the bottom. That'll be the time series associated with the decision process to recharge. And then over here, as you're watching these things move, watch this recharge meter, right? This is your phone battery going up and down over time. And keep in mind, we're inferring all this just from the trajectory data. This is what happens when we fit the model. Okay, here we go. The line itself, the trajectory, is colored by the charge level. Blue is charged, red is discharged. So as it's moving around, you can tell when it leaves that recharge patch, it will start to lose the charge, like this bit right here where it's on this longer journey outside of the recharge patch, and then it has to come back, charge up, and then it's got enough charge, it can go again. Okay, so that's kind of how it works. It works well in simulation. Frankly, we did this first, of course, as you do as a good statistician. We were stunned. I was actually stunned. I wasn't sure we'd be able to learn as much as we are from the data. Now, why does that happen? Well, there's a lot of structure in this model, right? It is mechanistic, but that's the beauty of it. We get a lot of extra power because we're assuming we know how some of these things work. There's a long history of an understanding about how physiology works, and I don't think we're breaking any major rules here. Of course, I hope there's ways to get even more mechanisms in these models eventually too. So now that we've seen that, we can think about, well, what about inference? I mean, it's kind of cool to look at those big plots as inference, but let's look at inference on some of the parameters. There's not many in this model. This particular model has one beta coefficient associated with movement itself when this is like the drift related parameter, the advection parameter. Being negative associated with distance to polygon just means that it wants to go back toward the polygon or the recharge patch when it needs to charge. That's what it means when it's negative. And we'll see this same sort of inference for the other two examples. An intercept in the recharge function itself. So remember, this is the physiological function over time that we're sort of doing this line integral to understand how it's responding. The charge process itself is responding to the environment as the animal moves. We won't worry too much about the intercept, but what we will see is that once it's in the polygon, we get some positive inference saying that yes, it's definitely charging while it's in there. These are just violins representing posterior distributions if you're not used to seeing those. Okay, so we can get the inference. It seems like it's working, doing the right thing. And we tested this out in a variety of other scenarios too. So that's the simulated example. Let's see how it works on some real data. So this is two examples. One is a mountain lion in Colorado. This is very close to where I used to live. And then the other one is an African buffalo. Two totally different types of species, right? They're both large animals, but one of them is a predator. One of them is an ungulate. The ungulate, of course, we expect to have different dynamics. And I'll tell you about that when we get to the African buffalo section. Let's start with the mountain lion because we've been on that theme kind of the whole time here. So the mountain lion, same thing. We're going to fit the same model. I'm going to put in some important things in the model. You're going to see very similar graphic and movie to what I showed you last time, but we'll see how it works with real data, and I'll try to narrate as it goes. This green region up here will be a recharge patch. How do we know where that is? Well, that's a kill site. That's where it's cached a deer. And this one has been ground truthed. So we know where that one is. Colorado Parks and Wildlife goes and tracks these down and finds out if there's actually a dead animal there or not in certain cases. And we can see that this is distance from the kill site over here in the gray region. So you can kind of keep track of that as it's moving around. You notice it's going to hang out in here for quite a while. And it's going to take a long walk, a really long walk for about a week out here. It can go for days without food, these mountain lions. Such a big meal. And that relates to the physiology of the animal, right? Totally different life history than an ungulate, for example. Mountain lions will store up all this energy. They will then go out and do the other life history stuff they need to do. If they don't find anything, they can come back to the original kill site, fill back up. They're not limited by water or anything else in this particular environment. Okay, keep an eye on it as it's moving around in here. Starts out blue. It's in the recharge patch, just as we'd expect it should. There's some uncertainty shown in both our estimation of the G function and the rho function. Those are just pointwise credible intervals over time. As it gets out there on that long journey, it decides to head home because it's running low. Gets back in the recharge patch, hangs out there for a while, eats up, rests, whatever it needs to do. Goes on another little journey where it loses a bit of its charge process. I'll just show it one more time here too. Keep an eye on when that decision point gets made that it needs to switch. For example, right about in here, boom, starts switching back into a different state. So it switches to the other model, right? It uses the landscape in a different way in that particular case. And that's all being inferred. So we can make some inference there. And you see the same sort of inference comes up, right? The cool thing is we did this with a lot of other covariates besides the one that I just showed you, right? And what we saw is when we compare them just using some basic model selection techniques is that this is the one that came out on top, which is really interesting. Fundamentally, mountain lions are energy limited. And so we see that here in this example. Again, responding to the distance from kill site in a negative way, meaning it heads back toward the kill site when it needs to recharge, and it's responding positively to being in the recharge patch, this kind of buffered region around the kill site when it is in there in terms of gaining energy. In this case, we know it's energy. You don't always know it's energy though. For example, what about the African buffalo? The African buffalo, it's an ungulate, it's totally different. Right? There's not, in Kruger, they're not going to be limited by food. They eat grass for the most part. Grass is everywhere. They're almost kind of top of the food chain. They're not a predator, they're an herbivore, right? But they're almost top of the food chain. Their only natural predators, lions, which are there, but lions don't mess with African buffaloes too much. Right? If you've ever seen the Discovery Channel. So, but they are kind of a very high frequency energy thing. They're always hungry, right? If those of you who are herbivores know that, right? You kind of are hungry all the time. So they're the same. That's not really an issue, but so that's not really limiting. But what is limiting for this type of animal in this particular environment is water. African buffalo can't get enough hydration out of their food only. They have to have open drinking water every day. That's a physiological limitation. It's well studied. So what we'd expect to see before we even fit this model, what we'd expect to see is this thing is pretty redlined. It needs its resource all the time. The other thing we'd expect to see is that something like recharge patch associated with a linear stream network would be really important for it. That's where it's going to find open surface water. So same framework as before. All the graphics on the left are the same order as they were before. Uncertainty shown in both our estimation of the G. Energy, in this case, hydration function, and rho, the decision function to recharge. You can see as this individual is walking around, it does not spend much time outside of those green areas, which is a buffer around a river network in Kruger. It'll come back on here. Go. So a couple of features of these data and the resulting inference is that this thing is redlined all the time. You notice the color is more red than it was for the mountain lion, right? They are constantly thirsty, and they need to be in this environment. And this is the wet season in Kruger that these data were collected. And so this helps us understand how they respond to water, how they respond to the environment when they are between having water. They have to really store up the water before they're going to make these long journeys between different branches of the stream network, et cetera. And you'll notice they really book it across those when they get a chance to.
What kind of time frame are we looking at here? Like, what's the kind of trajectory is this?
The beginning of the time series is 425. The end of the time series is 517. So about 3 weeks. Distance is on the order of miles. It's like tens of kilometers, not hundreds of kilometers. Okay. We can get some inference out of that, and big surprise. Real similar violin plots is what we had before, right? We got the right things in the model that we needed to get in there. We compared a lot of other things. These are the ones that rose to the top. So you've got, again, it knows where the water is. It's going to find water when it needs to in terms of recharge. And when it's in there, when it's finding the water, we know that it is because we see it in the resulting pattern in the trajectory data. The model sees it. This is a great example of statistics, right? You take the data and patterns that you can't observe with your eyes necessarily in the data. I mean, we could see it, just plot it in space. We can tell that they're spending some time in the green, but we don't know what's happening with their underlying physiological process while it's doing it. So this model helps us learn a bit about that and quantify it. So there's so many other things in animal movement I'd love to tell you about. I don't have time today, so I'm probably going to call it at the moment, and I'll leave you with this reference slide, but I'm happy to chat with you later today or now if we have time. And that's my last slide. Thanks.
Thanks, Mevin, for the very nice and visible talk. Are there any questions for Mevin at this point?
In terms of mechanism, mechanistic, and the way that things are used a lot in what exactly is the mechanism?
Yeah, this is a great question, right? So we will contrast phenomenological, meaning we're just modeling the patterns, versus something that we think we know how it works, either physiologically, evolutionarily, genetically, biologically, etc. If the more deep you get into talking with your colleagues in the biology department, the more you understand their version of mechanism is way more precise than what we use it in statistics. The way I kind of came up using that word is when we start to get fundamental mathematical equations in some of our statistical models that are not just regressions, that's when it starts to look more mechanistic, right? But our colleagues in biology would say, no, 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 no. When this protein manifests itself because of these two combinations of genes happen, that's a mechanism. So depending on who you talk to, you'll get a different answer for that, for sure.
Just a more of a clarifying question. So those recharge patches, is that something you always know ahead of time, or would there be interest in trying to estimate that?
Yeah, great question. So the recharge patch seems to be kind of the way we did things here, for at least for this demonstration. But of course, you could imagine it doesn't have to work that way, right? We could just put in a variety of different hypothesized landscape attributes and see what happens when we try to estimate their importance. Yeah, I wouldn't expect you'd know all the time.
That's sort of a related question. So does the shape of the recharge patch play an important role?
Yeah, to what extent the animal is allowed to stay in there is important, right? If you go back and you look at some of that bit from the simulation, where was that? Oh yeah, right in here. You notice it could take this really long journey in there and still stay within the patch, but move a lot. So in that case, yeah, sure. And you notice that in the stream network, they're allowed to walk up and down that stream network and still have access to water pretty easily before they leave. So in that sense, for sure, yeah. But whether the topology matters in some other fundamental way, I'm not sure. Yeah, probably.
You could imagine that there's multiple recharge processes happening on
Yeah,
one
right.
individual, say like, sleep and food or something.
Yeah.
And if sleep, they go to a certain place also.
Yeah.
Have you thought about that?
Yeah. Yeah, it makes tons of sense. This particular slide is perfect, right? You can imagine G being multivariate. That's the simplest way to do it. And that's the first way we wrote it down. And then we realized, oh, okay, we're getting in over our head. Let's just start with one and see if we can do that. That's the natural thing to do next.
Yeah, we haven't actually tried to fit something up there.
No, I'd love to do that.
Are there any other questions? Okay, well, if not, let's thank Mevin again for